Okay, good. So question 12 is perhaps a little bit trickier because you have to figure stuff out from the molecular formulae, and also actually there is more than one possible answer to this one, so don't panic immediately if you didn't get quite the same answer as I did. But anyway, the starting point is, I think perhaps the simplest way to start is with compound R, because that's the thing which can polymerize, and the key clue is that it tells you it can polymerize in two different ways. It gives you one product which can be hydrolyzed and is therefore presumably a condensation polymer, polyamide or polyester. The other one which can't be hydrolyzed and therefore is presumably an addition polymer. And that's the clue, because that tells you that you have to have an alkene group to do the addition polymerization, but you also have to have a carboxylic acid and either alcohol or amine, but given the molecular formula, which is C4H7NO2, it looks like an amine because there's a nitrogen there. So carboxylic acid group, an amine group, and an alkene group all squashed into that molecule. So that would be a good place to start. Now there is actually more than one possible answer to that, which is sort of a flaw in the question really. But here is one. So if we put the carboxylic acid group at one end, and then we can put the alkene group, and then we can put CH2NH2. Now that would be a possibility, because you can see, let's just turn that into an explicit carbon, and then if you count the atoms you can see that fits. You've got 4 carbons, 7 hydrogens, a nitrogen and 2 oxygens. So that looks like a possible candidate because it's got those 3 functional groups that we need. So let's have a look at the polymerization reactions of that. So the first one is the addition polymerization, which will make polymer T, because that's the one that can't be hydrolyzed by sodium hydroxide. So let's do that one first. So remember, with addition polymers, the key is to draw out the monomer with that format, because then it's easy to see what's going on. So we'll have H and COOH at one end of the alkene group, and then H and CH2NH2 at the other end. Notice there's an EZ issue there. It could be the other isomer, that's the Z one, but it could be the E one. You can't tell from the data that you've got. So you're going to need N copies of that to make a polymer, and then the usual thing for repeat units, you just draw the same thing but with the double bond opened out to make now the 2 linker bonds, but otherwise the same 4 things top and bottom. So H, H, COOH and CH2NH2, and that repeat unit is going to be repeated N times. Make sure your linker bonds stick out through the brackets, and that's your equation, and that's polymer T. So polymer S is the one which can be broken down, so that's the condensation polymer, and you can see we're going to get that by condensing together the carboxylic acid group from one monomer, condensing with the amino group of the next one. And what always happens then is that the carboxylic acid group just gets left behind with its carbonyl, OH is condensed out, and the amino group loses one of its hydrogens. So if we just redraw that monomer, I'll just draw it as a skeletal formula to save time. So there's the monomer, and again we're going to need N copies of that, and this is going to happen now under very different conditions, which is why we get a different polymer product. We'll get the condensation polymer, so the OH now is gone, and we just have the linker bond to the carbonyl group, and then this bit is the same, and then when we get to the amino group at the end, we now just have NH and then the linker bond that side. So the same as in all the other polyamides that you've done. That's repeated N times, so make sure the N goes down there to show that unit is repeated N times. And crucially, remember this is condensation, so each time you make one of those, a water gets removed, and so we have N waters produced as well. And so that is polymer S. So finally we just need to work backwards and figure out what compound Q was, which turned into that when it was refluxed with aqueous hydrochloric acid. So the conditions are a bit of a clue that it's some kind of hydrolysis reaction, and the other clue is that it lacks the two oxygens but has an extra nitrogen in it, so it's C4H6 N2 is the molecular formula. So that should all combine together to point you in the direction of thinking, oh yeah, this used to be a nitrile group, because remember, nitriles can be hydrolyzed to make carboxylic acid groups. So compound Q is simply the same thing but with C triple bond N at that end instead of the carboxylic acid. Everything else in the molecule is the same. And that simply is one of the key reactions that you need to know for nitrile groups, that they will hydrolyze when you reflux them with aqueous acid to turn into the carboxylic acid. And you can see that indeed that fits the molecular formula. So that's compound Q, and that's it. Now, as I said, there are other possible answers to this question, because so long as you have these three functional groups in compound R, then they don't necessarily have to be arranged like that. So there are actually quite a few possible answers. We've already talked about the EZ isomers being different, but you could also, for example, put the amino group there, make an alpha amino acid, and then you could just do this. And that would be fine, for example. So anything that has the correct three functional groups in it is okay as an answer to that question. And that is it.